In this lecture, we look at the second law of thermodynamics. This says that for any process in a closed system, the entropy S of the system never decreases. Mathematically, we can write this as the change in S is greater than or equal to 0. So this is one way of writing the second law of thermodynamics. For a reversible process, delta S is equal to 0. For an irreversible process, delta S is greater than 0. Let's look at the implications of this for the efficiency of a heat engine. An example of a heat engine is a gas that follows a closed cycle. Removing a heat Q sub H from a hot reservoir that's at a temperature of T sub H and depositing a different heat Q sub C in a cold reservoir at a temperature T sub C. In this process, work is done by the gas. For example, it moves a piston. Efficiency is defined as the work done, that's what we wanted, divided by the energy needed to maintain the hot reservoir. Typically, you need to burn some sort of fuel to maintain the hot reservoir at a high temperature to make this heat engine run. If we write this in terms of the quantities we're familiar, then the work done is this W, where we're using magnitude so we don't have to worry about signs, divided by the heat removed from the hot reservoir, Q sub H. An ideal engine has a delta E internal which stays equal to 0. Actually, any engine has that. But to make it ideal, we also require that only the heats and work have any energy in them. We don't have energy going off into any other quantities. We also require that the processes involved are reversible so that delta S is equal to 0. In this case, the efficiency of this ideal heat engine is given by this QH minus QC, where we've rearranged our first requirement on energy so that to find the work. So it's Q, the heat of the removed from the hot reservoir minus the heat removed from the cold reservoir divided by the heat of the hot reservoir. We can rewrite this as being 1 minus the ratio of the heat put into the cold reservoir divided by the heat removed from the hot reservoir. We can also write this in terms of just the temperature using the fact that it's reversible. Since delta S is equal to 0, we know that the entropy change of the cold reservoir, which is Q sub C divided by T sub C, has to be equal to the entropy change of the hot reservoir, which is Q sub H divided by T sub H, since there's going to be no change in entropy overall. So that if we use this, the efficiency is going to be equal to 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. Let's look at an example. We have two identical blocks that are at temperature 400 K respectively. The two blocks are put into contact, and after a long time, the temperatures of the two blocks are 290 K and 410 K respectively. Is this possible? It may seem odd. You usually don't expect to see a 300 K block get cooler and a hotter block get warmer, but is this against the law? First, let's look at energy. The heat of block 1 is equal to the mass times its molar specific heat times the change in temperature of block 1. So this is equal to the constants, M and C, times the difference between the two temperatures. The final temperature, 290 K, minus 300 K. This gives us a minus 10 K times MC. If we look at block 2, we have the same constants, M and C, times now a different delta T. That's equal to MC times the final temperature, 410 K, minus the initial temperature, 400 K. That gives us a positive 10 K MC. So one block ends up giving up energy, the other one takes it in, so there's no problem as far as energy goes. The energy is all conserved. The temperature is not changing very much, so we can use our approximation for the change in entropy, so that delta S is approximately equal to the heat divided by the average temperature. Let's look at the change in entropy of block 1. Well, that's the heat that we just calculated above for block 1 divided by the average temperature. which is minus 10K times MC divided by 295K, the average temperature, which gives us this minus 10 over 295 times MC. For block 2, we again have the heat of block 2 divided by the average temperature. The average temperature is now different, and the heat is different, so we have plus 10K MC divided by 405K. And that gives us the fraction of 10 divided by 405 times MC. So if we put the two of them together and add them, we have the first fraction plus the second fraction. And you might notice that the negative fraction has a bigger value than the positive fraction, so that when we add the two together, we end up with a negative number or something that's less than 0. That is not allowed by the second law, so we are breaking the second law of thermodynamics with this. And fortunately, that fits with our common sense that we were not expecting a cold block to get colder while a hot block gets hotter when you put them together.